Okay, everyone. Now we're going to be talking about implicit differentiation. Now, what is this exactly? So far in the course, for the derivatives that we've looked at, we've always found derivatives of functions of the form y is equal to f of x. Okay, so f of x is equal to something with respect to x. So we say in mathematics that when you have a situation like this is where y has been given as an explicit function for x. Even if we end up getting something like this equation, so say we're given 4xy minus 3x is equal to 6. We can rearrange this equation and isolate for y. Okay, so we can write this as, bring the 3x over, divide through by the 4x, and then we end up getting this expression, y is equal to 3x plus 6 divided by 4x. And then normally we don't call this y, we rename it to be f of x. But if we were to plot this function, remember, for every x value, we get a certain output, and we think about that as being somewhere along y, your y-axis. So you plot your points, and then you can draw your function. But what happens if I get something that, looks like this? Can I isolate for my y? Well, sometimes I can't, and sometimes it's just really hard and takes a long time. So because I can't directly isolate for y to get a function f of x is equal to something just with respect to x, what we say is that y is given implicitly in terms of x. Now, how would we differentiate this? So we use this thing called implicit differentiation, where we consider all y's, all of our y variables, to be functions of x. And then we use the chain rule. So everywhere we see a y here, we think about it as y of x to the 5, okay, yx cubed. So when we differentiate it, we're using the chain rule. We would bring down the 5, and then we would leave the inside. So 5y to the power 4, and then times the derivative of the inside, which is just dy dx. So that's the general idea behind implicit differentiation. If you don't see x's only and you have all these y's, you're going to have to use this method. Okay? Now, in terms of notation, make sure to think about your y like this. And when we say y prime, we mean dy dx. So for the first question, I want to find dy dx if I'm given this. So what we're going to do is we think about taking d dx of both sides. So I'm thinking of going d dx because I want to differentiate with respect to x. That's what having the dx on the bottom means. Okay, so I'm going d dx of my left side is 3x. And remember, this y is really a y of x. Okay, plus 4 y. It's really like a y of x, and then this is squared. Okay, so that's my one side, and we go d dx of the entire equation. So I'm also going to do d dx of my right side. So my right-hand side is just equal to 0. Okay, that's not a problem. Now let's look on the left side. So here, I'm differentiating with respect to x. I have to be careful because I actually have two functions. Right? I have a function right here. So this is function 1, this 3x. And then I have another function here. So for this, I have to do product rule. And then for this expression, my second term, this is going to be a chain rule. Okay, you don't have to write these things when you're doing your solutions, the stuff in the orange. Okay, but I just want to make sure that that's clear. So let's start off with the product rule. So the product rule says that I go d dx of the first times the second. Okay, I'm just going to write this as y, but if you want to write it as y of x, actually no, let's write it as y of x, times the second plus the derivative of the second, so d dx of y of x times the first. Okay, and that's all for the first term. My second term is, so ignore the 4 because remember, derivatives can go inside. You can think about it like factoring out the 4. And now start from the outside, work your way in. On the outside, we have a 2. Okay, so by chain rule, I'm going to bring down my 2. Okay, and then I have my y of x to the power of 1, and then times the derivative of the inside. So d dx of y. And then right-hand side, this is equal to 0. So now I'm going to drop the y of x. I'm just going to write them as y for this next part. So for the first one, what do we have here? So the derivative is 3 times y. Okay. And then I have plus the derivative of y of x. So this is just y prime, or in other words, dy dx. This is times 3x. And now over here, I'm going to write this as 4 times 2. So that's just an 8 times y to the power of 1. And then I have dy dx. This is all equal to 0. Now, something that you can do if you're concerned that you're going to make a mistake about the derivatives. Okay, I'm going to redo it in a different way. If you're concerned whether you're going to do the dy dx or the d dx properly, do it for every single variable. And what I mean by that is, for this first one, d dx of 3x. Even though we don't normally write it, remember what this means. This means 3 times dx dx times y, and then I have plus dy dx times 3x, and then we have plus 8 y to the power of 1 dy dx is equal to 0. And then everywhere you see dx dx, we just think about this as 1. So if you're concerned if you're going to do the d by dx properly, just do it for every single variable. Okay, that seems to help students a lot. Okay, so now that I've done that, I want an equation for dy dx. So what I have to do is isolate for it. So first, let's make this a tiny bit simpler. So I have 3y plus dy dx, and I have 3x of them here. And in this next term, I have plus 8y of them. And then this is equal to 0. So what I'm going to do is I'm going to bring this 3y to the other side. Okay, so dy dx times 3x plus 8y is all equal to negative 3y. And now I can just divide through by this. Okay, these are being multiplied together. So I have dy dx is equal to negative 3y divided by 3x plus 8y. And then there's my answer. Okay, so what did we do? We differentiated, and then here, after this point, we need to isolate. We need to isolate for dy dx. Okay, now let's try the next one. So I want to find dy dx for x plus root x root y all y squared. So what I'm going to do to make the power rule easier is I'm going to rewrite the things with a root as to the power of 1/2. And remember, everywhere we see a y, we think about it as y of x. What do? We start off differentiating d dx, both left side and right side. Okay, so now let's do term by term. So I have d dx of x, so this is going to give me dx over dx, plus, here I'm going to have the product rule, okay, because I have this term multiplied by this term, and they're both with respect to an x. So I'm going to have the derivative of the first, okay, times the second, and I'm going to drop the x here just to make it a bit easier. And then times the derivative of the second, so d dx of y to the 1/2 times the first. All right, that's good. And now on the right-hand side, start from your outside, work your way in. I'm seeing a squared here, so I'm going to have to bring down the 2. I have y to the power of 1, and then I have times d dx of the inside, which is my y. Okay, so now let's do the rest of the derivatives. So dx over dx, this is just equal to 1. Okay, so I have 1 plus, okay, d dx of this thing, so I'm going to bring down the half, 1/2 x to the negative 1/2, and remember, secretly, we always do d dx of the inside, which is just x. Okay, so this times y to the 1/2. Now, I'm going to bring down the 1/2 for the y. So 1/2 y, 1/2 minus 1 is negative 1/2. And the derivative of the inside, dy dx, bracket, bracket, times the second, is equal to 2y dy dx. Okay, this thing's just 1. Again, you don't have to do dx dx if you want, but I just find students make less mistakes if they just do the same notation regardless of the variable. Okay, so let's simplify this a tiny bit here. So we have 1 plus 1/2 x to the negative 1/2 y to the positive half plus 1/2 y to the negative half x to the half, and then I'll write the dy dx at the end. And then we have 2y dy dx. So I'm going to bring everything with dy dx on one side and everything else on the other side. So I'll leave the 1/2 x to the negative 1/2 y to the half plus, no plus, equals the 2y dy dx, and then minus this whole term. So 2y dy dx minus 1/2 y to the negative half x to the positive half dy dx. Okay, and now we want to isolate for this dy dx. So I'm going to factor it out on my right-hand side. Rewrite the left-hand side. So what do I have? Dy dx, the first term, I'm left over with a 2y. My second term, I'm left with a 1/2 y to the negative half x to the positive half. And then I'm going to divide through by this, and then I'll be able to isolate, or then I've isolated for my dy dx. So that's going to be dy dx, I'll zoom in a tiny bit, is equal to, so on the top we had 1 plus, now what I am going to do, actually I'll write it out first and then on the next line I'll do it. So x to the negative 1/2 y to the positive 1/2 all divided by 2y minus 1/2 y to the negative 1/2 x to the positive half. Okay, this looks not very nice. So we're going to have to simplify it. And for this time, you will see me switch back to roots. So what I'm going to do is write it as dy dx is equal to, now the top really means 1 plus, so on the numerator, I have the square root of y, and then I have a half, so the 2 would be at the bottom, and then I have the root of x divided by 2y, and similarly, I have minus, on the top, I have root of x, divided by, I have a half out front, so the 2 goes on the bottom, and then root of y here. Okay, and in order to simplify this, I have to simplify the numerator and the denominator separately. So I'm going to have a fraction on the top, fraction on the bottom, and then I can use that rule. If you have a over b divided by c over d, it's the same as a over b times d over c. And then it'll be much easier to write this out. Okay, so, all right, so common denominator. So I have 2 root x on the bottom. So my 1, I'm going to have to multiply top and bottom by 2 root x. And I'm going to make more room for myself. So 2 root x divided by 2 root x plus root y. So I can put them together in one term because of that common denominator. Okay, and then big divides, big divides. Now on the bottom, the fraction part, I have a 2 root y on the bottom. So I'm going to have to multiply the top and the bottom of this first term, 2y, by the 2 root y. Okay, so I have 2y times 2 root y. And then I have minus my root x. And then the common denominator is 2 root y. And now I'm going to use that rule. Okay, I'm going to rewrite this in a way that makes it much easier to read. So this is equal to 2 root x plus root y. This is divided by 2 root x. Okay, and then this is all going to be times by the bottom fraction, but I got to flip it. So 2 root y divided by the bottom. So this is going to be 4y root y minus root x. And we can simplify this slightly. Okay, so we have a 2 here and a 2 here. Because these terms are all being multiplied together, and there's only one term at the top and bottom, that's why I can get rid of the 2. And then I can factor this root y into each term here, and this root x into each term here. So what is that going to give me? That's going to give me 2 root x, root y, plus root y times root y, that's just y, divided by, so 4y root x, and then root x times root x, that's just x, and don't forget about that negative. And then there's our answer for dy dx. So the punchline, what's the punchline? So when we're doing implicit differentiation, you can think about it in 3 steps. We're going to differentiate both the left-hand side and the right-hand side with respect to x. But remember, every time you see a y, secretly it's a dy dx. Okay, so we think about it like doing the chain rule. For step 2, we put all the terms with dy dx on one side and all the other terms on another side. And then we factor out our dy dx and we isolate for it. Okay, so hopefully you found this helpful. We'll be doing some more problems like this on Wednesday.